we are four in the team. My name is Deepak, Pati, Lucas, and Adam, and we are going to present two works that we have done regarding machine learning and neural networks. One is on XNAR nets, and the other is a binary connect. The scope of our project is that we took MNIST set, which classifies digital numbers from 0 to 9, and then infers on them. So our scope is that we took a trained model, we learned that from another machine, and then got the weights, and then implemented in hardware how you infer from new inputs what the answer is going to be. And in this presentation, we are going to present the modules that we have worked on in both XNARNet and also the binary connect.
Before we start with how we implemented it in the hardware, I would like to explain how the big picture works. So consider an image size of 28 by 28 from the MNIST data. Now this image has to be classified in among the 10 classes that we have, which is 0, 1, 2, according to the number 0 to 9. So there are 10 classes back there. Each input image goes through 2 convolution layers, and this is 3 layers of fully connected network. So what happens in the convolution layer? If you have, is this visible to everyone? No, I'll explain it on that side. So, okay. So if this is the image, and this is your kernel, and this is the sliding window. This kernel is slid through the image throughout, and for each number there's a multiplication, and the kernel, they add up to get one number for each kernel. So the image itself downsamples here from 28 by 28 to 24 by 24. And in max pooling, instead of multiplying the kernels, we just pick out the maximum number of that. So it further downsamples the image from 24 by 24 to 12. Here, there are 20 different kernels, and further we use 50 kernels. So there's 8 cross 8, the image again downsamples at each layer. Here the number of kernels are 50, so the total number of images that we get is 50. This data keeps on getting populated, and in the end we get a vector, we get a matrix of tensor size of 50 cross 4 by 4, which we flatten out into a vector of size 800. It is then forwarded to the feed-forward network, fully connected network. Now, so this will just be the scope of our project, which is the fully connected layer. We're not doing any hardware simulations for the convolution part. This is how the computation is done. So the initial fully connected layer we had here was of size 800. So we have an input vector of 800 cross 1, which we multiply it with the weight matrix, which we, okay, before even proceeding to that, the whole neural network model is being trained on a different machine. This is for the inference phase. The whole hardware speed up that we are gaining is in the testing phase, where we're actually classifying new images based off of our trained model. So we already have a weight matrix W1 of size 500 cross 800, and multiplying these two, we get 500 cross 1 size vector, which was our hidden layer. And we repeat the same process with 10 cross 500, and we get a classification vector.
And in terms of the concrete implementation in hardware, it looks like these fully connected layers look like follows. So you have the vector coming from the RAM, in our case, because the test bench we have made is in the FPGA's RAM and the test bench, so it comes from the outside, and then it gets normalized, it then converts into a binary representation, and from that we get an alpha value which in our test bench case, we already have it. So we have the alpha value, which is a scalar, and it's a fixed point scalar in our case. And the vector value is binary value. And then we have the third thing, which is the matrix, that's also binary. And then it goes into, so you are doing matrix vector multiplication using XNAR pop count. And we'll go into it next, how you actually accomplish that. And then here, basically, you are doing the vector matrix multiplication. And then after that, the results that you get is a vector, and then you multiply it with the alpha scalar value. And then again, you multiply it with a beta value, since it comes from the matrix. Since the matrix, you have binarized it, and then you need that normalizer into the actual answer. And then you can loop back, but this is the one stage of the loop. And then you can reuse those values into the next layer. This is the first fully connected layer. The same architecture can be used for the next layer. So we are not doing a redundant copy of same units. That's why you see it up there, and then the controller then decides the new matrix or vector. And for binary connect, it's also similar, but in this case, instead of multiplying to multiplying two binary vector and matrix, we have one fixed vector, fixed point scalar, fixed point vector, and then the matrix is binary. And instead of using XNAR pop count, in this sense, we can use an accumulator, which does the same thing. And then it's pretty much similar. So to wrap up, in this case, these are the main modules that we've implemented in both cases. In XNAR Net, we have XNAR pop count, and in the binary connect, we have accumulator, which do the same thing, which is matrix vector multiplication. And then we have scalar multipliers.
So we have a couple different versions of the pop count we looked at. So what we're trying to do here is we're trying to take a value, or we're trying to take a standard logic vector in VHDL speak, a bunch of ones and zeros, and then find out how many ones are in that string. And one of the simple ways to do it is if you were to take just 2 bits from each string and then add those together, 2 other bits from those string, add those together, and so on and so on. So for a 32-bit word, you'd have 32 bits, you'd have 16 adders in this case. And then you have more adders to reduce it, and eventually you get the total sum of the bits. And once you're done counting the number of ones, there's an additional step that you need to do to determine the actual pop count, which is a combination of number of ones within your word and the number of zeros, which algebraically, you can just take the number of ones, double that, and then subtract the number of bits. So this was our initial pop count architecture, which is kind of slow because you're going through a lot of adders, in this case ripple carrier adders, so your propagation delay is quite large. The second concept we looked at was a LUT-based or lookup table-based approach. In this case, we would reduce the propagation delay by taking chunks of our 32-bit word and then applying a lookup table. Lookup table would simply look at the 4 bits, and then according to this truth table over here, spit out the value of ones within that little nibble. So you would do that, in the case of a 32-bit word, you do that 8 times, and then you would send the output of this lookup table to adders to end up getting the pop count result for all 32 bits. In this case as well, since we're just counting the number of ones, we have this additional step where you have to double the count of the ones and then subtract from the total number of bits. So we further optimize this and to our lookup table, which incorporates the true definition of pop count in accordance with this true table over here. So you can see we're counting the number of ones, doubling that, subtracting that by the total number of bits to get the true pop count. And this is what you need in order to get the negative values as well, in order to apply the complete XNORNet algorithm. So with this optimization, we saved 2 ripple carry adders, which we had in the previous design, and we have a combination of lookup tables, which apply a certain amount of area, but they give you the answer really quickly, along with the ripple carry adders, which don't take up as much area. So we coded this up into VHDL, so we have a simple 8-bit pop count design here. So this is the code for our lookup table in accordance with the truth table in the previous slide. This is basically what it looks like in Intu's complement notation for 8 bits. And this is a little comparison of the 3 architectures where we just have the ripple carry adders. You have more adders. The speed is slow since you have a large prop delay. All those adders also count for a large amount of area, so we're calling the area large. We had our simple ripple carry adder plus the lookup table. The speed is faster. The area again is kind of medium. With the optimized lookup table, we reduce a couple of those ripple carry adders. We just have 1 ripple carry adder, 2 lookup tables, so it's fast, and our area is reduced. And then this is our total pop count block, where we have our 2 lookup tables here, and then the ripple carry adder. So we created a test bench for this. It's just a test bench for the 8-bit pop count. And this has the XNOR functionality built into it as well. So we have several weights. You can see those in hexadecimal form on the very top of the screen. And then we have our input, our neural network input, which at this point we're looking at an 8-bit binary representation of that. So then we would take the XNOR of the neural network input and the weights, which would give our XNOR output. Then we would apply the pop count to the, we do the pop count of this. So the one I have highlighted, you can see 0, 1, 1, 1, 0, 0, 1, 1. So you have 5 ones and you have 3 zeros, so that will give you a pop count of 2, which is 2. And in this case over here, you have more zeros than ones, so that will give you a pop count of -2, which is represented over here.
These are the scalar multipliers. So from the previous one, you will get a vector, and then you have to scale it with the scalar value, which is the alpha or the beta in our cases. And since in VHDL you can multiply 2 scalar fixed point of the same types, this is an integer. The result is an integer, so we cast it to fixed point, and then we multiply it to get resultant vector scale. And this is a simple example in which we are just talking about 16, like 8 bits, and the 8 bits are the fixed points of the other side of the decimal. So this is not like 32, 8 one side, 8 other side, just for the explanation. ABs.
For the accumulator, basically every neural network needs a multiplication and accumulation operation. For binary connect, since we have the vector as fixed point and the matrix as binary, we kind of need just an adder. So this is algebraically, this is a multiplication operation, but it comes down to just simple additions and subtractions for each indices of the vector. So this is how the accumulator works. So we have weights coming in from here, which acts as a control signal for the adder. This is the input vector, and this is just a standard 0, so that we know that whether we're subtracting or adding for the first element. This comes here, the resultant is passed to another adder, and then the second index in the input vector comes in, like here. So this is the NNN, and NNN 0, 1, 2, and these are all the weights. So this comes as the intermediate weight result, and then this is passed to the next adder, getting 2.5. Now, based off of 1, it means addition, and 0, we have considered it as subtraction. So if the weight is, depending on whether weight 1, 0 is a 1 or 0, the subtraction or the addition happens. These form kind of a matrix of different adders, which I'll be explaining in the next slide. This is just a piece of code how it works. So every time we encounter weights for 0, 0 being 1, we add the two numbers, or if not, then we subtract it. This is how the schematic looks like. It forms a matrices of adders. This waveform is pretty much similar to what Adam explained for the pop count thing, but this would make more sense in the last slide where we'll compare the results with the Python code for the validation set. I'll skip this one for now.
Okay. Okay. During this project, we also tried to explore how we could really synthesize all this design and put to run in a actually FPGA. So in this front, we extended some models. We create more than one version of the same model and try to map to see how it's mapped the model functionality to the actual hardware, which resource it use actually in hardware. So we got, for instance, here the Scala multiplier. It was created initial version in VHDL, as Vibrak has shown, and we also created another two. First of all, this is how Scala multipliers works. We usually just to perform a fixed point multiplication, we consider both numbers as two complements and do just like 8-bit multiplies from the multiplicand, from the multipliers, multiplies each bit of the multiplicand. So basically is when you have 0 in this initial bit, you just add zeros here, and if there is 1, you shift because of the weight of it and place sums it to the form the next parcel, and if it's negative, you propagate the ones. So you can see that by the end of the day, you're gonna need to accumulate all these parcels, and so you can do this in 2 ways, or more than 2 ways actually. If you use just resources like LUTs and registers, you will need to on each clock cycle generate one of these parcels and start to accumulate. Or you can, for instance, this would be very latency, would introduce a lot of latency. Or you could, for instance, just create a huge mux and to generate each parcel in parallel and then sum them together, which use a lot of area. So we are exploring those things, and we try to map this in an actual Xilinx FPGA. We choose the Arctic 7 architecture that has this architecture with a lot of CLBs. I will talk what CLB are, and also a lot of other things more. But most important for us for this design are DSPs and CLBs. There's a lot of other resources like FIFOs, I/O, clock management, tiles, and things like that. So next slide. Okay, so each CLB is a configurable logic block, and they do have you can use them to implement your combinatorial function and also use flip-flops in them. And each CLB has 2 slices, and this is a picture of 1 slice. So you got a lot of 4 LUTs. You got some multiplexers, some carry chains if you are doing math. In this case, 4 flip-flops, and also another 4 flip-flops here. So this is the number of resources you have, and depending on how you design your model, those resources will be accumulated. You'll be using. Next one. So, and this is the in contrast with CLB, you also have DSPs. right? That you can also use instead of using CLB in those kind of, in a multiplication, for instance, in a scalar multiplication, for instance. DSPs are very are small blocks in FPGA, very dedicated for mathematical computations, where you already have in silicon a multiplier, a multiplier and accumulator. The accumulator is here. The adder, subtractor, and also bitwise logic circuits. And you have also dual registers where you can, and this register A has a pre-adder inside of it. The interesting thing is that the entire computation is done in a 3-stage pipeline, which means it actually running in full speed in 3 clock cycles. We're gonna multiply 2 numbers, which in that case, if we were using latest prone RTL design, we're gonna, for that initial table that we've shown, we're gonna get 5 clocks. If you are clock cycles, if you are multiplying 2 16-bit, you're gonna take 16 clock cycles. So it's a great advantage, and they also use less power. So this you can go ahead. So we decided VHDL version. We designed our 2 Verilog modules for the scalar multiplier to compare them. The VHDL version is actually based similar to the DSP result, the Verilog DSP results. So those are the 2 codes that these are just the snippets of the entire model. There's a lot of things, but there's just important things. So this always blocks is placed in a generate that generates 16 of them just to compute one element in the input matrix. The input matrix has 8 elements, and this is computing just 16 of it. Sorry. So this we are shifting here, like if you recall that multiplication matrix, table. We are actually shifting the input, the parcels left, and then back to the right. Right back to the left. Sorry. So it's basically what we're doing here, and this kind of design maps to CLBs. While this kind of design, where you are using the multiplier signal here, the synthesizer, well, the synthesis tool will map to the DSPs. And we are using just 8 of those always block because each one is actually the element of the vector that will be calculated to the output. So the result we had, for instance, for the area in a small device like just one scalar multiplier that uses a lot of area, we are using actually almost 5% of the number of LUTs, and most of the slices are using just LUTs, not flip-flops, because we are in a combinatorial circuit at the point. So we are actually we are wasting a lot of flip-flops that is in the slice, and we are not using them. In a lot of multiplexer as well, because there's a lot of ifs and things like that. And in the other hand, we have the DSP version that uses just 24 DSPs. And this is the device that we used was very small devices. There are devices in the market with more than 1,000 of DSPs. So the bottom plate is if we to really implement this in hardware and I don't know, bring it to market. We need to focus in and using as much as DSP we can. Yes, so.
All right, so I'll talk about the XNORNet results now. So this is our top level VHDL simulation where we had a test bench. We had some weights where we sort of implemented a RAM type of interface within our test bench. So every clock cycle we get a new set of weights, new set of neural network inputs, binarized at this point, an alpha and a beta to at that last stage of the flow chart that Biebrek showed. We will get back to that fixed point number. And this is what the neural network looks like after the pop count. And then this is what it looks like after the last stage, after all the multipliers. I think this is after the first multiplier, and this is after the second multiplier. And then on the next slide, we'll show how we coded up a basic Python script to compare the actual results with our hardware implemented results. So this is our Python script here in the top left, and it's using the same weights that we have for this clock cycle in hardware. We have the same neural network inputs, neural network outputs zeroed initially. We have an alpha and a beta for the scalar multiplier at the last steps. And we do basically the same thing that we did in hardware. So we have the XNOR operation where we do the bitwise XNOR, or in this case it's XOR, but we convert that to an XNOR over here. We come up with the true pop count, which can be positive or negative. We print that out, and you can see that over here. Then we do the scalar multiplier for the alpha, which is over here, and the scalar multiplier for the beta over here. So then what you can do is you can compare these numbers, and you can look at the 10 and 20, for instance, with the hardware simulation outputs. And that compares to these two up here. So you can see this is a 32-bit fixed point notation. We have 16 bits representing the integer, and then 16 bits representing the fraction. So 0, 0, 0, A, 0, 0, 0, 0. That just represents 10.0, which matches up with our results. And similarly, we have 0, 0, 1, 4, 0, 0. So that's 4 plus 16, so that's 20, which is what we see here. And then you can go along the line, and we can see that we match up perfectly with our simulation results.
So this is the slide which I skipped for Binary Connect. These are the results for Binary Connect. So this is a snippet of the Python code that we wrote for the validation set. And this, considering this one, which I highlighted, so it's a hexadecimal number with 8-bit. So the 4 part represents the integer part of it, and the rightmost 4 bits represent the fraction part of the decimal. So considering 0.0168000. So it's basically 16 to 0, 6 plus 8, 16, negative 1, 16, 1. So it's 16 plus 6 plus 8 over 16. Sorry. And this is 22, so this is the decimal here.
Yeah, the decimal.
So this is 22.5, which matches correctly here. 22.5. This is this one. So these are this was the validation set that we used, and that's about it. Do you guys have any questions?
Yeah, I have one question about, can you go to the pop counting slide? So,
This one?
yeah, so you implemented 2 variations of pop count, right? So the straight pop counting as well as you are using some lookup table to look the pop counting?
Yeah.
Yeah, so after the windowing, your image stripe, the vector size is like how much? How many bits does it have?
So we had 4 bits going into the 4-bit lookup.
Yeah.
And then
I was curious about so if you increase the window size or the kernel size, then this stripe would become larger, right? So then you will have to add many combination to the lookup table. So then there will be like, I don't know, there will be a trade-off between memory and,
Yeah, so we were thinking about that.
Yeah.
So I mean, you can make the entire 32-bit pop count as to one
Yeah, yeah,
giant
yeah.
lookup table, but that would take up more area
Yeah,
than
yeah.
is
So
in your
More
FPGA.
CPs.
so then it will be easier to do the pop counting straight rather than looking up to the lookup table.
So there's a trade-off where you
Yeah,
can
yeah,
probably
yeah, I understand that.
yeah.
Yeah.
We were thinking about that
Yeah,
too.
yeah, yeah, yeah.
Good point.
Yeah. Other than that, I mean, it's impressive. Like you have done a lot of work. So.
So for the last two slides, the verification part, are these the synthesis, the FPGA result, just some ISIM result?
This is an ISIM result, so it's an ISIM test result of our test bench implementing basically one iteration through the hardware, and we compare that to the power.
Okay. And for the FPGA synthesis one, synthesis result,
Yeah.
these are only some multiplier.
Yeah, because this was the model that could directly be mapped between or using DSPs or using CLBs. So that's why we choose this model in particular to experiment with different implementation.
And you are only presenting some area result. How about the frequency?
Yeah, since we didn't implemented, right? We synthesized it, but we didn't implement it to the device. Actually, we do not have any result on frequency, on propagation time, but I'm confident that DSP is the best approach for this. Also, it would be very interesting also to get the power consumption of those two. I fully agree. But yeah, we went up to the synthesis.
Okay. Can you summarize your own work in this project? Yes.
Like each of us.
Yeah.
So I mainly worked with so I started working with the test benches on the different implementations that the paper talked about for both of them, like Torch and PyTorch scripts. And I tried to, I started off creating, with Bibrook, I started off creating with, to implement the whole neural network using PyTorch and Torch. So the original paper talked about Torch, and there was a PyTorch implementation on it for simplicity, because the original thing talked about the Lua scripts. But for some reason, we were able to implement the PyTorch thing, but not the Torch thing. So the problem with the PyTorch was that we were not able to extract the binary matrices and the vectors. They were giving us floating point numbers. So we couldn't use those numbers directly from in the form of VRAM that we could do. So that's why then we dropped them off and we just generated random numbers and tested the math if it's working. After that, I worked on the accumulator module, which I explained.
So I worked on the XNOR pop count, I did the hardware design for that, as well as the top level integration of everything, and helped out a little bit with everyone.
I worked more on the synthesis part and helping on the implementation in Verilog and VHDL. Yeah, and how it could actually get together and be synthesized in FPGA.
I worked on the vector scalars and also some part of the XNOR top-down, in the sense how you know that the vector multiplication is working. And the previous unoptimized version, and then, so most of it was done by LM, and some I have less part.
Beaver pointed out a small error that I had in the hardware, so
Which led then to the optimization.
Okay, thank you very much.